Okay, so if you look at these, we use the activity series to fill these in, and we get magnesium is more active than cobalt, so we make magnesium 2+. Magnesium's always a 2+. It's aqueous and cobalt solid. We have chromium reacting with tin 2. Chromium can be a 2 or 3, but out of ease, we just make it chromium 2 plus tin. Barium plus tin 2 nitrate gives barium nitrate and tin solid. And copper plus hydrobromic acid is no reaction because copper is less active than hydrogen, so copper can't cut in on hydrogen. Now, the last thing we have left to discuss in this chapter for redox chemistry is reaction with molecular oxygen. Oxygen is an oxidizing agent, which means it gets reduced. It goes from an oxidation number of 0 in the element in its natural state to -2 in most compounds. So it's getting reduced because it oxidizes other things. And combustion is a type of oxidation reaction that we look at quite a bit. When we have complete combustion, it means that we have plenty of oxygen, so we make carbon dioxide and water. Now, for the purposes of this class, you will be expected to know what combustion is going forward, and I will expect that if you come across a homework problem in any future chapter and it says during the combustion of whatever, you can write the equation for whatever compound plus oxygen makes carbon dioxide and water. You can write that equation and then balance it. To balance this one, we need 2 oxygens and we make 2 water. So this is complete combustion. We assume we have complete combustion most of the time. Incomplete combustion happens when we have limited amounts of oxygen. And when we don't have enough oxygen, we don't make carbon dioxide. We make carbon monoxide gas plus water. And again, we need to make 2 waters, and we need 1.5 or 3/2 of oxygen here because I'm restricted on the amount of oxygen I have. And if we really limit the amount of oxygen, we don't even make carbon monoxide. We make carbon solid plus water. And this is when something's burning really badly and you see all that black sooty material. That's what this is. You're just not getting enough oxygen in there and you're making that soot, which is basically carbon. So this is something to think about in everyday life. A lot of my students feel like chemistry is just something hard you do to get your transcript in shape. But this is combustion chemistry is part of your everyday life. You drive to school or ride a bus in a combustion engine vehicle, right? And you have a furnace to heat your home. That furnace has an air intake, and there's a furnace filter in there. Usually this time of year, you hear on TV, they're reminding you, change your furnace filter and replace the batteries in your smoke detector. You change that furnace filter because when it gets plugged up, then you don't get enough oxygen going in your furnace, because it's sucking in air from the ambient surroundings, and when there's all particles and dust and things, it gets in that filter, and as the filter gets clogged up, you don't get enough oxygen, and then you start making carbon monoxide in your furnace, which is not a good thing in your house. And the same thing can happen with your vehicle. In Michigan, you drive off the road in the winter into the snowbank. You need to get out of the car, clear the snow away from your air intake and your exhaust so you don't build up carbon monoxide when you're running the engine waiting for the tow truck. Question? It is. And again, it's usually because of lack of oxygen. If you have a fire and you don't have it properly laid, you don't get enough airflow through the fire and kind of between the logs. Okay, that's why they teach you the basic H and the A-frame fire in Boy Scouts and Girl Scouts. Okay, good skills for everyday life. So sometimes we have compounds that contain sulfur, and when we burn them, we need 9/2 oxygen to balance this out, we have ethyl sulfide, and we have 9/2 oxygen. We make carbon dioxide and water, but we also make sulfur dioxide. And as you've probably heard through your earlier classes and public outcry about burning high sulfur coal, that when you make sulfur dioxide, it can react with water and make sulfurous acid, which is acid rain. So that can be a problem, and we try to avoid that. And then the last type of redox equation that's just kind of descriptive is when we have metals or nonmetals reacting with oxygen. Metals reacting with oxygen make metal oxides. An example of this would be something like sodium. If we have sodium reacting with oxygen, it makes sodium oxide. And then when we take this sodium oxide and we dump it in water, you would expect that because it is an ionic compound that it would break apart and give sodium ions and hydroxide oxide ions. You'd expect sodium and oxide. That's not what you get. What happens is it reacts with the water and you make sodium hydroxide. Because it's actually reacting with water, it's not just dissolving. And so these make bases. When we have nonmetals, things like carbon reacting with oxygen, we make nonmetal oxides, carbon dioxide or sulfur dioxide. And then these nonmetal oxides can react with water, and when they do that, they make acids, like carbonic acid or sulfurous acid or sulfuric acid. So there's a lot of chemistry going on that is redox, not just single replacement. And in your text, they talk about stoichiometry and redox reactions. I don't discuss that in this chapter because the examples in there are just like the examples we've already done previously. We talked about ionic equations in chapter 4, and we looked at some examples there. So redox equations aren't any different than any other equation. Once it's balanced, you look at the mole-to-mole ratio, and you do stoichiometry the same. So I don't think it's special. The only thing that's special is balancing those redox equations. And when you look at that, you have to remember that we use that process. And I understand that there was some confusion about some of those equations on Wiley Plus because it looked like they were written out and it said hydroxide ions plus this plus this. When you balance those, the hydroxide tells you it's going to be in base, but don't put them in there when you try to balance it. If you try to take those and balance them on inspection with those hydroxides or hydrogens in there, you will never do it. You need to break it into two half reactions and just go through the process and know that it's in base. Okay? So that's how you do that. Okay, so on the next page, you'll see kind of a fancy problem, and we'll go through that one next.